In this module, Module 15, we're going to talk about some other building blocks, particularly multiplexers and decoders. So multiplexers, we'll also call these muxes, or mux for short. So multiplexer, mux, and decoders. So we'll define what these do, and then talk about various implementations and uses, and then I'll also show how to use these building blocks, muxes and decoders, to perform logic functions. So these are combinational building blocks. The output is completely determined by the value of the current inputs. So what's the combination of inputs that we have? So muxes and decoders are particularly useful building blocks, so we're going to focus on those for this module. A mux, a multiplexer, selects between one of n inputs to connect to the output. So here is the symbol for the multiplexer. It's showing that we're going from many, or several, in this case 2 inputs to a single output. So it shows that kind of going from more to fewer. It's always going to one output. In this case, we have 2 inputs, and there's this other input called a select input. And this is a control input. That select input is going to control how the other inputs get fed to the output. So our other inputs are D0, data input 0, and data input 1, D1. And so when select is 0, the input D0 gets fed to the output. So when select is 0, D0 gets fed to the output Y. As you might expect, when select is 1, well, D1 gets fed to the output Y. So when the select line is 1, D1 gets fed to the output Y. So it's basically routing either D0 to the output Y or D1 to the output Y. So another way we could write this truth table is we could write it as select line D1, D0, output Y. Well, when the select is 0, it doesn't matter what 1 is. It's going to follow whatever D0 does. When select is 1, it doesn't matter what D0 is. The output will just follow whatever D1 does. Or, even more condensed, as shown here, when select is 0, Y is equal to D0. When select is 1, Y is equal to D1. How would we build this? Well, we can write sum of products equations, as we've been doing up until this point. We could write it from this truth table, the more condensed truth table, or the even more condensed truth table. I'm going to go ahead and write it from this truth table, this intermediately condensed truth table. So we're going to look at the ones here. Again, sum of products. We're going to say Y is equal to, well, this first one here is S bar and D0. So if S is low and D0 is high, we're going to get a 1 on the output Y. Or this next one, if S is 1 and D1 is 1. So here we have an equation. I'm going to now show how we could have gotten that same equation from this more condensed truth table. Well, when is Y going to be 1? Well, if select is 0, so Y is going to be 1 if the top row, if select is 0, well, that S bar indicates that select is 0, and, well, D0 has to be 1. What's in the output has to also be 1 in the output column. Or the other way to make Y1 is if select is 1, so S, and D1 is 1. So either going from the truth table with don't cares or the truth table that has variables in its output, or we could have gone from the original expanded truth table using a Keymap, for example, or Boolean algebra. We're going to get the same equation. So how do we implement this? Let's go ahead and write our equation on the next page. Y equals S bar and D0, or S and D1. Well, two-level logic. That would be pretty easy. We can say, let's put our S here. We have S and S bar, D0 and D1. We have two AND gates to make our product terms, followed by our OR gate. We have S bar and D0, or S and D1. That looks pretty good. We also have, written it just as long as we have straight lines. Inputs could have come from the left as well. So D0, and S bar, or S and D1. That's one way we could draw it. So way 1, way 2, both are acceptable. And turns out there's a third way with tri-state buffers. Well, tri-state buffers, remember, tri-state buffer has an enable up here that allows the input to flow to the output only if the enable is true, is 1. And so we could actually, if we put a bubble on that enable input that inverts it, and we put the select line coming in from the top into this top tri-state, and I'm going to draw that line through and have that select line. This is still the S select line, select signal, coming in to that bottom tri-state buffer. And then we can tie the outputs together just because only one of those tri-states is enabled at any given time. Put D0 on the input there and D1 on the input there. Well, when S is 0, so in the case that S is 0, this tri-state is enabled and drives the output Y. This tri-state is cut off because it has a 0 on its enable input. If, however, S is 1, well, then D1 gets fed to the output Y. And this tri-state on the top is cut off. The input is cut off from the output. So here, drawn out nicely, and I show the Keymap method of finding the equation. So here's our circuit, the internal circuit of our multiplexer. Couple options here. Which one's right? Well, they're both right. Generally, using tri-state buffers for logic is not recommended just because of delays. If for some reason this tri-state buffer is more delayed than this one, we could have contention on the output or a floating output. But logically correct, this is probably the preferred implementation with the AND and OR gates and inverters. Again, after we have designed or implemented the multiplexer, we can now abstract it away and just use the symbol We could dive deeper into the abstraction if we needed to, but now we can go to a higher level of abstraction and say we have a select line, D1, D0, or we'll do it in the same order shown up there, D0, D1, and sometimes these are labeled 0, 1, and the output Y. This is called a 2-to-1 mux, because it has 2 inputs and 1 output. We're always going to have 1 output. So 2 inputs and 1 is the number of outputs. We're always going to have 1 on that. We could also have other muxes. So let's say we wanted to choose between 4 different things. So D0, D1, D2, and 3. Well, how many select lines do I need now? Well, I have 4 things I want to choose from. So I need to have 4 unique values on the select line. I'm going to need 2 select signal bit 1 and select signal bit 0. So I need 2 wires on my select line to be able to select between either 0, 0, input 0, 0, 1, input 1, 1, 0, input 2, or 1, 1, input 3. This is called a 4-to-1 mux. We're choosing between 4 different things. This is the number of inputs. So if we wanted an 8-to-1 mux, how many select lines would we need? Well, log base 2 of 8 is 3. We'll need 3 select lines to choose between 8 different things. 0, 1, 2, 3, 4, 5, 6, 7. So this one is an 8-to-1 mux. And in general, for an n-to-1 mux, we're going to need log base 2 of n select lines. So it turns out we can use multiplexers not just to select between data inputs, but we can also use muxes as a lookup table. So a lookup table means for each input combination, I'm basically going to look up what the output value should be. So here I have my truth table. I'm basically going to look up for the 0, 0 combination. Well, I want to have a 0. All right, there we go. Tie that to ground. Remember, that's the ground symbol, ground. And for the 0, 1, I want to have the output to be 0. For 1, 0, I want the output to be 0. And finally, for 1, 1, I want the output to be 1. Remember, that symbol is the sign for high voltage VDD. For example, VDD could be equal to 5 volts or 3.3 volts or whatever. So VDD, or this is our 1. Okay, so we look up, essentially use the mux as a lookup table. We put A and B on the select lines. When A and B are 0, 0, for example, we're going to feed whatever tied to the 0, 0 input to Y. Well, there we go. We wanted it to be 0, so we tied that input to 0. So we're using our multiplexer as, in this case, it's implementing the AND function. But we can change these inputs and get a different function. So, for example, let's do a different function. Let's try, for example, the XOR function, 0, 0, 0, 1, 1, 0, 1, 1. XOR would be 0, 1, 1, 0. We take our multiplexer, our 4-to-1 multiplexer. We have our 2 select lines. We tie those to A and B. So I can write this in binary, 0, 0, 0, 1, 1, 0, 1, 1. Our output gets tied to Y. 0, 0, I'm going to show a different way of doing this. I'm going to tie that to 0 or ground. 0, 1, I'm going to tie that to 1 or VDD. 1, 0, also tie that to 1. And 1, 1, I'll tie to 0. So I could have written it that way, or I could have written it, like here's another way to do it. This, A, B, 0, 1, 2, 3. And for example, I could have tied these to, instead of using the logical values of 0 and 1, I can use the physical voltages of ground and VDD. So these two are equivalent, these two versions of the implementation. So again, we can use our multiplexer for logic. Well, is this using less gates or fewer gates than what we had with our just an AND gate or an XOR gate? Well, certainly not. We just implemented our multiplexer. Could you implement a 4-to-1 multiplexer? Yeah, in a very similar way as we did with the 2-to-1 multiplexer. Use our sum of products form of the equation, write it out, and then turn it into 2-level logic is the simplest way. Well, so we've clearly used more gates here than we would have used with a simple gate level implementation using a single AND gate for this one or an XOR gate for this function. But there is an advantage here. The advantage is that I can change the function. I don't have to change the hardware, just the connections of the inputs. So I can change the function from an AND gate to an XOR gate just by changing what I tie the inputs to. So now we're going to try to use a smaller multiplexer to implement this function, this equation. So let's see how we would do that. Well, we can use a 2-to-1 mux instead. Let's write our equation here again, 0, 0, 0, 1, 1, 0, 1, 1. Now let's go ahead and do the AND gate example. And so now we're going to have a multiplexer. It's 2-to-1. Output's still tied to Y. But now I can have a single select line instead of 2. So let's suppose we put A on the select line. So when A is 0, it's going to take whatever connected to this input and feed it to the output. So when A is 0, what do we want to feed to the output? Well, no matter what B is, when A is 0, we want to feed 0 to the output. When A is 1, well, those cases, those two rows, we're going to feed, it's going to select this input and feed that to the output. Well, what do we want to feed to the output at that point? Well, when A is 1, the output follows whatever B does. When B is 0, the output should be 0. When B is 1, the output should be 1. So we can just tie that input to B. So when A is 0, output's 0. Great, exactly what we want. When A is 1, if B is 1, the output will be 1. Good, A and B should be 1. If B is 0, though, A is still 1, but if B is 0, the output Y gets 0, just as we wanted. So even with 4 inputs, we can use fewer or a smaller multiplexer. Here we're using a 2-to-1 multiplexer. And we can write that truth table condensed like this. I'll have A and Y, 0, 1. When A is 0, output Y should be 0. When A is 1, the output Y should be B. And say, well, I don't want any gates. And so I can just read, that's the original equation. So I can now just read from that truth table and say Y is equal to, well, the only way I'm going to get a 1 on Y is if A is true and whatever is in that Y output column. Y is, A has to be true, A is 1, and B has to be true. Now we are here back to our original expression of Y equals A and B. So here we have that process written out. So Again, when A is 0, we want to see what the output should be. Well, it should just be 0, independent of B. When A is 1, what should the output Y be? Well, at that point, it just follows whatever B does. Could have used B in our select line. Show that process as well. Could use B in our select line, and here we have our 0 and 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, and now we want to put B on our select line. So when B is 0, which rows do we look at? Well, B is 0, we look at those two rows. Well, Y is 0, no matter what A is. When B is 1, well, B is 1 in those two rows. Now, Y is just going to follow whatever A does. If A is 0, Y is 0. If A is 1, Y is 1. So if B is 1, Y should be A. And we'll tie our inputs to our inputs of our multiplexer to ground and A. The second circuit that we want to talk about, this is a common combinational building block, is the decoder. The decoder has n inputs and 2 to the n outputs. And the outputs are what's called one hot. And that means one hot or one high output at once. So the outputs in this case, Y3 through Y0, only one of those outputs will be 1 at any given time. And this one is called a 2 to 4 decoder because it has 2 inputs, number of inputs, and 4 is the number of outputs. In general, it's going to be n to 2 to the n decoder. So if the inputs A1 and A0, if they're 0, 0, Y0 will be high and all the other outputs will be low. If the inputs are 1, the 1 output, Y1, will be high and all the other outputs will be low. If the input combination is 2, Y2 will be high, all the others low. If the input combination is 3, Y3 will be high and all the others will be low. So it's a decoder in that it's really decoding the binary value of the inputs. So if we have Y or A1 to 0, the A input is 2, for example, well, then that means that Y2 is going to be high. It decodes the binary value of the inputs. Well, decoder implementation. We go to our go-to method of sum of products. Here we have a 1 in Y0. That's the only one we get. Y0 is A1 bar and A0 bar. Y1 is A1 bar, A0. Y2 is A1, A0 bar. Y3 is A1 and A0. And so we could use our gates to easily implement those values. And you'll notice that Y0 is really minterm 0. Y1 is minterm 1. Y2 is minterm 2. And Y3 is minterm 3. So we can implement our decoder. Here's an example implementation. Y3 equals A1 and A0. Y2 is A1 and A0 bar. Y1 is A1 bar and A0. and Y0 is A1 bar and A0 bar. So it turns out we can also use our decoders for combinational logic, for implementing logic functions. So here we have our decoder. If we put our inputs A and B on the inputs, we could have written these outputs as output 3, 2, 1, and 0, so the decimal interpretation as well, if that's useful for you. But we can see that these each, as I mentioned before, are those outputs Y3 to Y0 are really the minterms. So if, for example, I want to implement the XOR function, here's our XOR function, then I can just pick off those minterms where, well, XOR is A and B, or A bar and B bar. So when A is 0 and B is 0, well, Y0 is going to be a 1. I'll get my 1 on my output Y. When A is 1 and B is 1, well, here we go. We're going to get a 1 on Y3, and that will give me my output 1 on Y. In every other case, in the 0, 1 case, well, this output's a 1. All the rest are 0, but not connected to that one. Or 1, 0. The Y2 output is 1, but that OR gate isn't connected to it. So let's do another example. Let's say we have a decoder that, let's go ahead and do a XOR function. Let's say we have a 2 to 4 decoder. Again, 2 to 4 decoder. We'll put A and B on the inputs, and we want to do XOR. We want to say Y equals A XOR B. We could write that in sum of products form, A and B bar, or A bar B. Remember, XOR exclusively one of the inputs is 1 to make the output 1. So A bar B or AB bar. And we're going to get our decoder outputs, Y3, Y2, Y1, Y0. So 3, 2, 1, 0. When you're doing logic, 3, 2, 1, 0 is easier to see as the binary values, because you're looking at the truth table, 1, 1, 1, 0, 0, 1, 0, 0. So we want to pick off the minterms, minterm 1, and OR that with minterm 2. So we can use decoders for logic. We can also use our multiplexers for logic. We can, do another example of a decoder. Let's do this is example 2. Here's our example 1. Let's go ahead and do another example. Example 3. Using decoders for logic. Let's say we have a 3 input function, and I'll just make a random function, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. I'm going to pick some random function here. In order to implement this, we're going to use a decoder, a 3 to 2 to the 3, or 3 to 8 decoder. Input 2, input 1, input 0. We have A, B, and C. This is our 3 to 8 decoder. And we'll get I'm going to write this in the same order as the truth table to make it easy. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1 outputs. Well, I'm going to first put my OR gate down here. I'm going to OR together these minterms. And I want minterm 1, minterm 2, minterm 4, 5, and 6. So I want to OR all of those minterms together to get my output y. So I'm going to pick off minterm 1, minterm 2, ORed with minterm 2, minterm 1, minterm 2, minterm 4, minterm 5, and ORed with minterm 6. So I can use a decoder to implement, well, some arbitrary equation, add an OR gate, and then pick off the outputs that I need, the minterms that I need for that function. So let me show some more examples for using multiplexers to implement logic functions. So let's say we have some function. The easiest way to do this is to implement it with a 3 input, so 3 inputs on the select line. And we'll take this, we'll use a multiplexer that has 3 inputs on the select line, A, B, and C, select line 2, select line 1, and select line 0. And then we have inputs D0, D1, D2, D3, 4, 5, 6, and 7, and our output y. So this is input 0, 1, 2, 3, 4, 5, 6, and 7. And we can tie our inputs high. So here we have, this one should be high. Input 3 should be tied high. And 4, 5, and 6 should also be tied high. And then the remaining inputs should be tied low. So, for example, when A, B, and C are 1, 0, 0, well, our high voltage will be fed through input 4 to the output y. Likewise, when the input is 1, 1, 1, this low value will be fed to the output y. So we can also use a smaller multiplexer, just like we did before. So let's reduce this to, instead of an 8-to-1 multiplexer, here's our 8-to-1 mux. We could use, for example, a 4-to-1 mux. Well, now we can only have 2 values on our select line. So let's try A and B on our select line and output y, 0, 0, 0, 1, 1, 0, 1, 1. So the 0, 0 AB input combination is there. We can see that our output y follows C. Let's put C there. 0, 1 are in those 2 rows. Again, the output y follows C. Now we have 1, 0. Well, the output y is just 1, no matter what C is. And finally, we have last combination 1, 1 on A and B. And output y is 1 when C is 0, and 0 when C is 1. So the output is C bar. So we could have also chosen different values on our select lines. For example, instead of A and B, we could have chosen A and C on our select lines. Well, it's a little bit harder to see from the table, but we could still do it. A and C are 0, 0 in that row and this row. Well, in that case, independent of what B is, the output y is 0. A and C are 0, 1 in these 2 rows. Independent of what B is, the output y is 1. A and C are 1, 0 in those 2 rows. Independent of what B is, the output y is 1. And finally, A and C are 1, 1 in those two rows. And the output Y, well, when B is 0, the output is 1. When B is 1, the output is 0. So the output is just B bar.